Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. My guest today is Adel Djellouli, Ph.D. He has a Ph.D. in applied physics. He's part of the Bertoldi Lab at Harvard, and they're working on a programmable liquids, which should be very, very interesting, also called Metafluid. So, Adel, welcome and thank you.
Hi, Richard. Thank you very much for this opportunity, and thank you for inviting me.
Yeah, tell me a bit about your background and how you got to work with these special fluids.
My background started where I was born. I was born in Algeria. It's a country in North Africa. I studied there up to when I was 21. After I did the army, I went to France, where I did my bachelor and master and then PhD in applied physics. And then after that, I joined Harvard in 2018. Yeah.
Okay. Well, very good. What led you to work on these special metafluids? Was that what your PhD was about, or how did you get into it?
A bit of both. I would say that what brought me to work on this metafluid is having a coffee with a colleague. That's how it started. This idea of a metafluid was brewing in my head for a long time because I did my PhD on harnessing elastic instability of a spherical shell. So basically we make a soccer ball, if you want, a tiny soccer ball, swim just by making it collapse on itself and then cycle that. So it collapses, it comes back, comes back. And just this simple geometry is able to swim and generate thrust at all scales. And so that was my PhD, and I worked on a single sphere. And I was always wondering what would happen if you put many spheres together. And
what do you mean a single sphere, like a bubble, or like a bubble with fluid in it? What do you mean, a solid thing?
Imagine it just like a soccer ball. So you have a shell that is made of a very deformable material, and that shell encloses air. It's a hollow sphere. And what happens is that when you put this hollow sphere in let's say a liquid, and then you impose cycles of pressure, so you increase the pressure and then you decrease it cyclically, what happens is that this shell, after you reach a certain critical pressure, is going to collapse on itself. So it becomes like a ball, if you want, a ball of soup. And then when you remove that pressure, it comes back to its spherical configuration. And doing this motion in a fluid make the sphere swim, basically. So we are harnessing something that we call an instability, a discontinuity, if you want, and we make something useful out of it. Usually up to, I would say, 2010, this kind of instabilities is something that we didn't want in real life because we call it buckling, this instability. And you can think of buckling as you take, for example, your ruler and you compress your ruler and you see that your ruler bends at a certain moment. And imagine that happens in a building, well, the building collapses. So civil engineers for a long, long time worked on trying to understand this failure mode and put a number on, okay, when does it happen? And they do that for beams, like for rods. They do that for cylinders, for rockets, for example. And they do that for spheres or hollow spheres. And so this paradigm changed or shifted in early 2010, thanks in part to Katia Bertoldi's work, where she, among others, like Pedro Reis, for example, they harnessed this instability to do something useful out of it and not just try to avoid it. And so in continuity to that spirit, if you want, we took a sphere, hollow sphere, and then we now harness this instability or this buckling instability to do something useful, which is swimming. And the property of such an instability is that it breaks symmetry. And if you want to swim at a really in a viscous fluid, let's say you are trying to swim in a pool of honey. Well, if you do your regular motion that we do when we swim, it's not going to work because it doesn't really break symmetry. So what you need to do when you're swimming in a viscous medium is you need to have a breakage of symmetry. So biology allowed organisms to do that through evolution, and they found mechanisms to do that. But if you want to make an artificial swimmer, and especially an artificial micro swimmer, breaking this kind of symmetry is very, very hard. This instability gives it to you for free. So we used that to make a hollow sphere swim at big scale, and then we did it at small scale. And that was my PhD. And I mostly studied the fundamental part of it, which is, does it swim or not?
What do you mean? Like, how do you create this bubble or this sphere, and then how do you stimulate it so it collapses or moves or swims?
So the way you do that at big scale, so let's say it's a centimeter scale or the inch scale for the American audience, you do that by molding. You mold two half spheres that are hollow, and then you glue them together, and then you have a ball, basically. You have a hollow sphere. And you make that out of rubber, because rubber is elastic enough that when it collapses, it can come back. If you do that with metal, for example, or a ping pong ball, then it doesn't work because you get plasticity and it gets damaged permanently. But with rubber, it can regain its initial shape with no problem. And that's the key, actually, to harnessing these kind of instabilities, is use materials that are elastic and they don't get into the plastic regime. And so the fabrication side on the centimeter scale is pretty straightforward. The fabrication at a smaller scale, that's trickier. So, and the reason why it's trickier is because I tried to do that for 6 months while I was here, and I failed miserably for 6 months. I was trying to do that every day. And then I talked to someone and they said, hey, I'm trying to do this and whatnot. He said, yeah, sure, I'll do it. And he did it for, in an afternoon, he was done with it. And that's one of my co-first authors, Yang Wang. And then we developed a really good friendship after that because we were working closely together.
How did you stimulate this to move? What did you do?
So there are two ways of doing it. You apply hydrostatic pressure cycles. So you imagine you put it in a syringe, you block the syringe, and then you move the piston up and down, you're creating these pressure cycles. But if you want to go at smaller scale and you want to go faster, one way to do that is through ultrasound. So the same thing that is used to image babies in the womb of their mother can be used in this technique. So you just use ultrasound, and that ultrasound is basically sound. Pressure is basically sound, or sound is basically pressure waves. So you can use ultrasound, these high frequency pressure waves, to stimulate these shells.
Is it a pulse that stops, or is it a continuous,
It's a cyclic
go back and forth?
It's a continuous cycles. So you send a pulse, which goes up and then down, and then you do another one, up and down, up and down, up and down. And what happens is when you do the up, the shell moves forward, and when you do down, the shell moves backward, but very little. And so you have a net displacement that is positive.
Okay. What has this evolved into now? What are you trying to do with this programmable fluids?
So that's the unit cell. Think about it as the Lego piece. So you understand the Lego piece and you say, hey, now that I understand the Lego piece, what if I put a lot of Lego pieces together? What can I do with that? And so when I was in Grenoble, I didn't have the chance to pursue this idea because I graduated and whatnot. But when I came here, it was always in the back of my head. And then I met with Ben Goysen. He's one of the co-authors, and we had coffee. And we talked about our ideas and whatnot. And we came up to, hey, this is something that we have in common, because he was also thinking about the same thing. And so we decided that I'll take care of the experiments, he'll take care of the simulation, and we'll explore this new system, and we'll make a metafluid. So for your audience, maybe I need to go one step back and maybe explain what's a metamaterial first, and then we go to metafluids.
Yeah, sure.
So materials in general, the stuff that you find in nature, they derive their properties from their molecular composition, the atoms that they're composed of. And you have a limited set of atoms. With metamaterials are artificial materials that derive their properties from structure rather than molecular composition, meaning that you engineer the unit cell. It's a bottom-up approach. You engineer the unit cell so that the bulk, when you put all these unit cells together, the bulk now has properties of that unit cell. And so for a long time, this was done in solids, and it was pioneered in optics, where people tried to make meta lenses. Have you heard of this term before?
Metal lenses?
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
Yes.
No, what does that mean?
Meta lenses is that you take regular lenses that you have in, let's say, in your glasses, and they're basically half an inch thick, let's say. You take that half an inch thick glass and you make it into 100 nanometers thick surface that does exactly the same thing as the half inch thick glass. And then you can think, hey, what can I do with this? Well, now, if you deploy, let's say, satellites in space to do observations, the payload is going to be much lower because you reduce the thickness by a factor of 100,000 in terms of thickness. So that's a big advantage that was discovered in the optical field. And they also managed to get sub-wavelength resolution. When you try to do, let's say, regular microscopy, the features that you can resolve are mostly limited by the wavelength of the light that you use. And so when you use visible light, let's say it's between 400 nanometer and 800 nanometer, meaning that if you have features that are smaller than 400 nanometers, you cannot image them with visible light. And there was a work pioneered here at MIT where they showed that they can develop a set of lens, if you want, or an optical system that allows you to go and resolve features that are 50 nanometers with visible light. And that's a big...
How do they do that?
Basically, they stack materials together, and these materials have certain properties that allows them to have a negative emissivity, for example. And if you tweak these materials in a certain way, then you can get properties that allow you to image or to access part of the light field that is not accessible when you image with regular microscopy, and that's the near field that has information that cannot be accessed when you...
So you don't need electron microscopy, you could use photons instead?
In general, you use these photons, either visible or not visible. They have a certain wavelength that get excited at a certain wavelength when they travel. And so when you use visible light, that wavelength is between 400 nanometers or to 800 nanometers. To try to resolve features that are smaller than that, what they do is that they move to smaller wavelengths, which is the X-ray or ultraviolet, but that's more dangerous. Let's say if you're trying to operate in a less safe environment, it's more costly, and it limits what kind of samples you can image, because you need to do vacuum, it needs to be dry. So you cannot use, let's say, that in biology, except if you do some extra steps to freeze your sample. And so this technique that allows you to do super resolution microscopy is given that for you for free, basically. So you can use your optical system tweaked a bit with this extra lens, and that allows you to get to super resolutions that are not available with regular microscopy. But that's one aspect of things, and I think that was pioneered in 2009, 2010.
What's the lower limit of resolution for a system like that?
I have to say I don't have that on the top of my head, but from the papers that I read, they were able to resolve features that are around 50 nanometers. I'm not sure if they tried to do anything below that.
Okay.
Yeah. And so that's for optical metamaterials, but the most exciting stuff is basically cloaking. What does it mean? Cloaking is you hide objects from, these objects they're there, but when you put a certain material around them, you don't see them anymore. You see through them, just like the cloak of invisibility in Harry Potter, for example.
Do you have like a layer on top of material that's, let's say, sub 50 nanometer features, and so nothing can really resolve it when they look at it? Or like, how does it work?
It just looks transparent. It looks as if you're seeing behind it, basically. It's just exactly like, have you seen Harry Potter?
Yeah, I've seen it.
He has this nice tool or nice cloak that allows him to hide, and basically when he drops into it, you see through him, even though he was behind this cloak. So they do exactly the same thing in optics, using these optical metamaterials by growing some features on the material or poking holes in a certain way so that they modify the way light is scattered and trick you to think that there is nothing behind. You're seeing through the object, although the object is there. And that's pretty cool. I think for now, it's still at the small scale, so maybe you can clock things around the micron, and it depends on the orientation of light and whatnot, but it's a huge breakthrough. And that's mostly, all this metamaterial has been pioneered in optics, and they advanced the field a lot. But optics or light is a field, right? And you can think, okay, if I replace light with an acoustic field, or if I replace light with a thermal field or a mechanical field, I could maybe do the same thing. And this is where Katja Bertoldi, the professor with whom I work here at Harvard, she made a huge impact in the community, where she basically pioneered this mechanical metamaterial realm, where you take a regular material, you change its structure, and you give it properties that don't exist in nature. For example, if you take regular materials and then you make a block out of it and then you compress it, when you compress it in a certain direction, it gets thicker in the opposite direction, it gets fatter in the opposite direction. Well, if you modify the structure of the block, you can harness this instability, this mechanical instabilities, or this buckling, if you want, to make it shrink when you compress it. So that's what we call a negative Poisson coefficient, and that doesn't exist in nature. And so you can harness this kind of capability by tuning your Lego structure. And if you design the unit cell in a certain way, you can control how the material behaves when you load it. So you can control its loading properties, and you can tune it or inverse design it so that you can, if you want a certain behavior, you can find what is the unit cell that will give you that behavior.
Yeah. So put a thin film over it, a layer that you control, or can you control like the bulk module?
You control the bulk, basically. And the way you do that is by poking holes, for example. If you poke holes in your material in a certain way, following a certain grid, then you can give that new material or the new structure interesting properties. You can also think about origami, the Japanese art form. It's a piece of a sheet of paper, and you fold it in a certain way. And these folds, for example, if you do it in a certain way, you can make that paper have certain properties that are not accessible to regular materials that don't use this folding technique. And it's a big field now, these mechanical metamaterials. You can do it also by introducing cuts in the material.
What are some of the practical applications, like in plain speak? What are some things being contemplated or tested besides the cloak?
So at least on the mechanical side, the applications are mostly around locomotion, for example. You can make things crawl, and you can make soft robots. Soft robots do complex tasks that if you use regular robotics, it will be much more difficult for them to achieve, or more complex, let's say. Here you can harness these kind of properties to achieve locomotion, achieve swimming, achieve grasping in interesting ways.
How long do you believe it'll be until there's commercial applications for some of the stuff you're working on?
Oh, there are already applications. For example, in helmets. There's a company here in Cambridge, Cambridge, Massachusetts, that harnesses this buckling instability into helmets to absorb shocks, for example. So it's already there. And meta lenses now, at least in the optical field, meta lenses are soon to be on your phone. So
what will they do there?
They will allow you to have less bulky optical systems. And that will allow you to achieve better resolutions and cheaper also. And it's less heavy. So you can do more complex things in less space, let's say.
Okay. Well, very good. So Adel, what's the best way for people to find out more about your work? Where can they go to see it?
So what I talked about now is MetaMaterials, right? Metafluid, we've been working on it for 4 years now. And the best way to read about it, there's a nice summary that Harvard Seas put out there for the press that basically summarizes our finding. And there's also the Nature journal that's under, behind the paywall. But if you guys or your audience want to get access to it for free, they can just email me. I can send them a copy. No problem.
Okay, very good. Well, Adel, thank you for coming on the podcast. And it sounds really, really interesting, the stuff you're working on. I appreciate you being here.
Thank you very much. Thanks, Richard.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.